Hello everyone, my name is Denisa McDonald and I'm presenting the collaborative work between Drexel University and Worcester Institute of Technology, Interaction with Touch-Sensitive Knitted Fabrics, User Perceptions and Everyday Use Experiments. Textile touch sensors can be constructed through digital weft knitting using a single conductive yarn and only two external connections. The sensors are based on capacitive touch. A capacitor is created between the carbon-coated yarn and human skin, since they are both conductors. Different design forms can be created, as illustrated in the three sensors in this figure. This demo shows how approximate location of touch can be detected by these touch-sensitive fabrics. They are created by interlocking conductive yarn, carbon-coated nylon, with non-conductive yarn, polyester in this case. The interactive areas are determined by the design, and other designs are also possible. Illustrations include detection of both tap and swipe gestures with some accuracy. The contributions of this work are the following: results from a qualitative study investigating user perceptions of this technology, design guidelines for potential applications, investigating the feasibility of simple gestural recognition, and results from everyday use experiments such as sensor stretching and laundering. We conducted a formative study with the following objectives: to understand users' views and experiences regarding interactions with this technology, to explore application areas into which users would want this technology integrated, to identify potential concerns when engaging with it for further study, and to generate design guidelines for future interactive applications based on touch-sensitive fabrics. The study was structured as 8 focus groups with 2 to 5 participants each, for a total of 32 participants. There are 3 design phases which approximately match the objectives of the study. In the first phase, users are introduced to the technology, its basic working principles, and only the touchpad designs in the bottom left figure are shown. Participants are then asked to discuss their initial thoughts. In the next phase, users interact with several design prototypes, and their usability is discussed, especially compared to any existing technology with a similar functionality. The samples are illustrated in the rest of the figures. We can see several examples of familiar interfaces, such as an alphanumeric keyboard, a piano keyboard, a volume controller, etc. Finally, in the last phase, users are encouraged to share more ideas, concerns, and suggestions. The data is then analyzed using thematic analysis, as a result of which the following themes emerged. The themes resulting from this study can be broadly categorized into general user perceptions, which were related to the soft fabric texture, the feelings of comfort it elicited, its robustness, affordability, and portability. And then relevant application areas, including wearables, smart environments, education, art and entertainment, medical and assistive technologies, as well as monitoring and activity recognition. Implicit in many of these mentioned applications was the need for this technology to support accurate gesture recognition, which we investigate subsequently. The third category is user hesitations and concerns, which focused on damage and safety questions, washing and drying of the sensor, stretching, and its exposure to outside conditions. We start to explore some of these everyday use concerns through experiments in the last section of this work. Gesture input is investigated on a volume controller-shaped knitted touch-sensitive fabric to see if the signals are different from each other for some simple gestures such as half swipe, full swipe, double swipe, and in addition, random contact samples, emulating accidental touch events, which are common in everyday life. The swipe gestures are illustrated in the figures in the slide and the accidental touch events in the short clip. The plots in this top figure illustrate gesture signals over time. The data was collected from one participant performing the 4 different gesture types, 20 times each, and is meant to provide an intuitive understanding of the trajectory of the signal, expressed as 2 frequency gain values over time. We can see the sample of the same gesture type follow a very similar path, more clearly shown in the top plots. These plots also illustrate how different gestures follow distinct trajectories from each other. Even random contact samples emulating accidental touch events seem to be more similar to each other than to any of the swipe gestures. The generated heat map is a more comprehensive analysis of all gesture samples from 12 users. It indicates gesture distances, computed using the sum of distances of all gesture sample pairwise comparisons. We can see that the gesture samples of the same type are more similar to each other than samples from different gesture types. And that is true also for random gestures, which tend to be more similar to each other than to any other category, showing promise for real-world use of this technology, as in a real application, we can ignore anything that we identify as an accidental touch event. Many applications of these sensors are wearable, which means that the fabric component of each sensor would need to be washed for appropriate use in real-world settings. This experiment demonstrates the change in the resistance of the fabric after 5 cycles of washing and drying with 3 different sensors. These results show that the percent change in resistance compared to baseline in all the trials does not exceed 70%, which are promising results for these conditions. Stretchability is another inherent property of the knitted fabric. In this experiment, the change in resistance due to stretching the sensor is considered for 2 cases, vertical and horizontal stretching of the sensor. Then those results are compared with the baseline state. 3 different sensors were tested for this experiment, and results vary with the structure of the sensor, starting from a 2% change with bigger sensors built more sturdily with more knitted layers, to 27% for stretching thinner and smaller sensors, which is to be expected since their structure changes more due to stretching. This variability, however, needs to be considered when designing applications for each specific knitted pattern and should be included in the computational models for accurate real-world functionality. Through our user studies and experiments, we have moved closer to having knitted smart sensors ubiquitously integrated into everyday environments, similarly to regular fabric. Thank you for listening, and please refer to our paper for more in-depth explorations of these topics.